Now let us continue to have the notations again. Earlier we did this for the binomial, and now for Black-Scholes model as well, we look into the notations. 0 is always current date in the timeline. T in the timeline is the maturity date. S0, time left to the maturity, is also called T. That's ST. So 0 is always like the starting line of the what we call the timeline. K, as usual, famously known for the strike price of the option. S0 is the current price of the stock, while ST is the stock price at the T at the maturity. Well, we have got this mu or the sigma, small sigma. The mu is expected return continuously compounded. The sigma is the volatility of the stock annualized. R is as usual risk-free interest rate expressed with continuous compounding. C for call price and P for put price only for European options. That's why it's small c, small p. That's quite straightforward. Okay, here's a celebrated formula. Look at this very carefully. Based on the Black-Scholes model, what is the price of a call? Look at it. Small c equals to S0, the current price of stock, times ND1. There you are. Normalized distribution of D1 minus present value of the strike price K E power to the minus RT times by ND2. You have got two things which you have to calculate on a preliminary basis before you can plug it into this equation. That is where n is the cumulative standard normal distribution and x is the probability under the standard normal distribution of the observed less than or equal to x. And look at the d1. Of course, you can express it in many ways. d1 is 1 divided by sigma square root of time t into natural log of current price over the strike price S0 over K plus risk-free return plus 1 over 2 sigma square, the entire thing times by the time. If it's 3 months, it will be 0.25. Once you can calculate these carefully, once you get the D1, then the D2 becomes easy. That is D2 equals to D1 divided by the standard error of the entire thing, that is sigma square root 2 times T. Or you can interpret it the other way around. Okay, the celebrated formula is, as you saw just now, the call price is S0 ND1 minus KE power to RT minus RT times ND2. For put, look at this. The minus, the present value of the strike time ND2 comes to forward. There, that comes front. Then you minus S0 times ND1. So you have KE power of R minus RT and minus D2. Now it's no more ND2, it's N minus D2. It's not very difficult to get the minus D2. It's same like the probability formula you found. Minus D2 is just 1 minus D2. If you know what's the value of ND2, then it's just 1 minus the value of ND2 will give you N minus D2. Many times students used to ask me, sir, why you didn't give me the table for less than 0 or the minus sign, the negative signs? No, don't worry. I can just give you for above 0. When you get the one for ND2, just 1 minus ND2 will give you N minus D2. Minus S0 for put times N minus D1. So this is where the equation for D1, more simplified, you can straightaway calculate natural log of S0 divided by K plus R plus sigma squared divided by 2 times T. But of course, natural log S0 divided by K is one side plus this fraction, that is a risk-free rate plus sigma square divided by 2 times by t, then you add it to the natural log S0 divided by k. The entire thing is divided by the standard error, that is the standard deviation times square root of t. Okay? Then once you get that, actually you don't have to worry or refer much to D2 equation, where you can just straight away play about with the D1 minus sigma to times square root of t. That's it. Okay, I think it's quite simple to understand this. We'll work out a numerical example, then you will know. Understanding the NX and standard normal density function is okay. You don't have to do much on this. Okay, applying the PS formula. Okay, look at this example, a numerical example. The stock price 6 months from the expiration of an option is $42. Right now, the stock price is $42. This option will expire in 6 months. That's how you construe this thing. The exercise price or the K, I've told you many times, strike price also can be referred as the exercise price, is $40. The risk-free interest rate is 10% per annum. There you are. The volatility is given here. The volatility, not the implied volatility, is the normal historical volatility, is 20% per annum or 0.2. So now you can check it out. Compute the price of a call, the call and put. Let us calculate for call. Notations first, you line up the data. S0 is $42, K is $40, R is 10%, standard deviation or volatility is 0.2, time is 0.5 because it's 6 months. Okay. First compute, there you are, the step by step. The first thing to do is compute D1. That's the first gear of the car. Once you compute D1, then you can use the D1 to calculate the D2. Okay, let us see how to calculate the D1. Okay, ND1. D1, not ND1, D1. Natural log of 42 divided by 40 plus 0.1 is the risk-free return plus 0.2 is the standard deviation squared divided by 2. The entire thing here, the second part of the equation, times by 0.5 because that is the time, divided by 0.2 the standard deviation, square root of 0.5. Try to use your calculator and compute this till you get 0.7693. This is D1, not ND1, D1. So once you got the 0.7693, you can use that to minus 0.2 times by the square root of 0.5. You will get 0.6278, that is D2. So successfully you have computed D1 and D2. Make sure you take a calculator and work with me. Then you know, because many students, they make mistakes here. The natural log 42 divided by 40, you have got the natural log button in your calculator. You will get a decimal placed figure there. Eh? Then you have to calculate this separately. Plus, that here you have to compute this part first. 0.2 squared divided by 2 plus with 0.1, then you times by 0.5 and add it to the 40 natural log of 42 over 40. Then you divide it by 0.2 multiplied by square root of 0.5. You should get 0.7693. Once you get that, this becomes easy. Okay, this is D1, D2. So now, look at here. Understanding the standard normal table. You have been given a normal table. To study the normal table, you have to identify a certain number, then only you can calculate that. See, ND1 now. From D1, you want to calculate ND1. You take the first two decimal places of this D1, that is 0.76. So, and 0.76 is what you have to record in the table. I'll show you afterwards. Plus the last three decimal points here, 93. Last two decimal points, that's 9 and 3. Plus 0.93 times one step higher and 0.77. Now this you got it as 0.76. Now you do the interpolation, the in between one. N times 0.77 minus N times 0.76. So it's equals to what? 0.764 you would have found in the table, and 0.76 is 0.7764 plus 0.93, and the difference here, the 0.77 is 0.7794 minus 0.7764. You calculate the entire thing, you will get 0.7792. That is ND1. And as you got the D2, you use the D2 in the similar way. The first two decimals, the 0.62 is N 0.62 plus the last third and fourth decimal is 0.78 times one step higher from 0.62 minus 0.62 and 0.62 because of this calculation, and you get it as 0.7350. Let us see the table now. Don't be too concerned about accuracy. More or less around there is acceptable. Okay. So once you get that, if you are asked to calculate the put price, then it's all minus. That's what I told you. N minus D1 is just 1 minus ND1. Because 1 minus 0.7792 will give you as 0.2208. And N minus D2 is again 1 minus ND2. You get it as 0.2650. Okay, this is the table. We call it the N table. So when you look at this ND1, you got the N 0.76. So how to interpret this is that you go into this N 0.76. You look for 0.7. Look at the row 0.7 and go to the 0.06. There you are. There, 0.7764. In the row of 0.2 under the Z column, and couple it with the column of 0.06, where you're looking for 0.76. 0.7 coupled with 0.06, you get it as 0.7764, right? That is why you get that figure there as 0.0064. There you go, 0.7764. You're not looking for this red color one, you're looking for the value of the N 0.76. Then 0.93 is given, and you have to look for N 0.77. What is that? 0.7. Just go one step higher from 0.06 to 0.07. So it's 0.7794. And you plug it in here, 0.7794. There you go. Minus 0.7764. That's the interpolation. So 0.7764 plus 0.93 times this difference should give you 0.7792. You are not going to refer for anything on 0.7792 into the N table. You are just calculating how to convert the D1 into ND1. So similar to here, ND2, you got N 0.62. So in the table you go to 0.6 and couple it up with 0.02. That is 0.7324. You see there? 0.7324. There you are. And you have got 0.63, just one step higher. 0.763, 7673. So you got it as 7673. Oh, no. You're looking for N 0.63. You look at 0.6 and go to 0.03, that is 7357 is given. Okay, so the entire thing is computed to 0.7350. I think it's quite straightforward. Now once you got that values, look at here, how to plug it in into your main formula called So you got it as S0 times ND1 minus KE power of minus RT times ND2. Okay. The call price is $42 is the S0 times 0.7792 what you have computed as ND1 minus 40 discounted by 0.1 times 0.5 times by the ND2 should be giving you $4.76. That is the call price. If you use the put call parity, you can calculate the put price, but if we ask you to apply the BS formula to calculate, then that's it. P equals to K e to the power of RT times N minus D2 minus S0 to N minus D1. So you already calculated that. So you discount the strike price or the excise price $40 to the continuously compounding power of 0.1 times 0.5, then times it by n minus d2 which is 0.265 minus the current stock price is $42 times by n minus d1 0.228 should be giving you $0.81. Look at that. The call price is $4.76, while the put price of the same stock is 0.81, which shows that implying that it's a bullish market. That's why the call price is expensive compared to put. You can also check your answers using put call parity. If put call parity is satisfied, then you can be rest assured the answers for the call and the put is perfectly correct. Okay.